So we want to make sense of the following diagram. Yeah, we have to still define the morphism of sheaves from f of u to g of u and the injective map from f of u to the direct product of its stalks. So we start by proving the injectivity from f of u to the direct product of stalks. So start with let f be a sheaf on some topological space X. So we fix a topological space X. Yeah, then you fix open sets of X. So U are all the open sets of X. And we want to show that the following map is injective. F of U to the direct product of the stalks. So this is very important, because now you can think of a sheaf in terms of stalks. So this map is injective. So there is not much in the proof of this definition, except that you should know the definition of a germ and you should know the uniqueness part of the argument of definition of sheaf. Yeah, so you should understand what the uniqueness part of the sheaf definition is. So you can recall that now before you look at the proof. So you fix f element of f of u, and suppose that the germ of f is 0 at each point x in u. So that essentially means you take f element of f of u and it maps to 0 in each of the stalks fx. Yeah, so if you have different points fx1, fx2, fx3, f get maps to 0. So for injectivity we have to show that f itself is 0 to start with. Yeah, so for each point x in u, by the definition of it being a germ, there is a small neighborhood around this point x which we call as v. X lies in this neighborhood, and when the function f is restricted to this small neighborhood of x, it is 0. Yeah. So this is true for all x in u. So for all x in u, because you have all these stalks where this map where f gets mapped to 0. So if at all these point x there is a small neighborhood, and on that f gets mapped to 0. Now u is a union of all these small neighborhoods. Yeah, because u consists of all these points x. You take a cover or a small neighborhood of x, take their unions, and you end up covering entire u, because you have covered all the points in u. Yeah, I'm going to write x for Vx just to make sense of the union. So we write Vx as a neighborhood of x. Now we just use the uniqueness axiom. Yeah, so f is 0 by the uniqueness axiom. Yeah, f is 0 on each open set ux. So on each of the covering sets f is 0. So it is 0 on the entire set u, and that is what the uniqueness axiom was. If you are 0 on all the open sets, then you are 0 on the union of those open sets. Yeah, so you have a cover, you are 0 on that cover, on each set of that cover, then you are 0 on the set for whose covering you had the function as 0. So there is nothing much to say, it's just the parsing through the definition, and the entire argument is u is covered by these neighborhoods of x. Now we are talking about definition of pre-sheaves. So f and g are pre-sheaves on x, and we want to talk about morphism of pre-sheaves. So morphism, say phi from f to g, consists of morphism of abelian groups. So you have the following morphism of abelian groups. Say f of u to G of U. Yeah, the morphism, we call the morphism as phi of U. Yeah, so we just name as phi of U just to remind you that the morphism depends upon the set U which is open in X. So for every set U you have a morphism. So there are like infinitely many morphisms like this. For a morphism of sheaves, for every open U you have this morphism. Yeah, so you have this group homomorphism. And you should also have a commutative diagram. Yeah, you have a set V contained in U. Then you obviously have this map since F is a sheaf. You also have a map in terms of GU to GV, the contravariance you can notice. Yeah, because F and G are sheaves. And the morphism means that you have the morphism phi of U here. You have the morphism phi of V here. So this diagram commutes. Now there is a natural restriction map from U to V in sheaves F and rho prime U to V in the sheaf G. So this diagram commutes. Yeah, rho and rho prime are just restriction maps in F and G respectively. Yeah, so that is pretty much it. So for every open set U and V, you have something like this. So if F and G are sheaves instead of pre-sheaves, we end up using the same definition. Yeah, we use the same definition for morphism of sheaves. Now this morphism is an isomorphism if there is a two-sided inverse. So this morphism becomes an isomorphism if there is a two-sided inverse. So what does this two-sided inverse mean? We will just write it down so that it is clear. So you have a map from F to G and then you end up back in F. So composition of these two maps is ID. So this composition is ID. And now instead we can go from G to F and then back to G. You again get an ID map. So phi and var phi are inverse to each other. On this slide, we want to talk about proposition 1.1 on page 63 of Hartshorne. So this proposition just says that a morphism or an isomorphism of sheaves can be characterized by the isomorphism at the level of stalks. So isomorphism of sheaves, if and only if there is an isomorphism at the level of stalks. So let us write this down. So you first fix a topological space X and then you talk about phi being a morphism from F to G. Yeah, so this phi is an isomorphism if and only if the induced map, the induced map at the level of stalk, this is a isomorphism. So phi p is an iso. So phi is an iso if and only if phi p is an iso. So this goes back to the previous slide where we drew that commutative diagram. So we are talking about isomorphism of two sheaves can be discussed at the level of stalks. Yeah. So let us prove this. So one direction is clear. Yeah. So if F to G is iso, you obviously have Fp to Gp is an iso because you just take direct limit at every point and you get a isomorphism. Now the other direction is slightly involved. Here also injectivity is easy. So this be a morphism of sheaves. So I'm writing homomorphism just because f of u to g of u could be a group homomorphism. So this is just a morphism of sheaves such that we have iso at the stalk level. So we have an isomorphism here. So we are given there is an isomorphism at a stalk level and we want to prove the isomorphism at the sheaf level. So at the sheaf level we know the morphism of sheaves is nothing but f of u to g of u. So we have to show f of u to g of u. This is a isomorphism for every set u which is an open subset of X. Yeah, so we are essentially talking about morphism of sheaves. So you should not worry about the word homomorphism I have used. It is just to say, just in case there were groups, but we always talk about morphism of sheaves. So first thing is to show injectivity. So you have the morphism of sheaves. So say an element f of u gets mapped to 0 in g of u. Yeah, so that the germ of f at each p in u. Yeah, so the germ of f at each p in u gets mapped to 0 in g of p. Now we have an iso. So we have an iso like this. Yeah. So the 0 will get carried to 0 in f of p. Yeah. So if phi of p as an iso, something is 0 in gp, it will be 0 in f of p because phi p is 0. So the germ of f is 0 at each p in u. Yeah, this we have written before, I am writing it again for clarity. So you have carried f from gp to fp and you are 0 again there at level of stalk. Yeah, but by the previous lemma there is this injectivity map from f of u to f of p, or the direct product of f of p. So since you are 0 in f of p, you have to be 0 in f of u. So let us make this argument simple by a diagram. So we go from f of u to g of u and we have these two maps. So if I take direct product at f of p and g of p, then the map fu to direct product of f of p will be injective as before. So we start with map f here. You took a section of the abelian group of f of u, it gets mapped to 0, thus it gets mapped to 0 in g of p. This map is an iso, you get 0 here. Now it is 0 at every point here, and by the injectivity argument it is 0 to start with, and that is what it shows injectivity. The next is surjectivity. Yeah, we have to show that this map phi of u is surjective. Yeah, which is a morphism of groups f of u to g of u. So phi of u is a group homomorphism, or you can just say morphism. This is surjective. So you have to take an element g in g of u and find an element f in f of u which maps to g. So you pick an arbitrary element g in g of u, and our goal is to find the corresponding f. So we obviously have no option but to go via Stalks, because we know we have an isomorphism at the level of Stalks. So take it to its germ gp at the stalk g of p. Yeah, so this is be the germ at p. Naturally now we have to go back to f of p via the isomorphism phi of p. Yeah, so let us write down this isomorphism f of p to gp via map phi of p. Yeah, so you have map gp here. So it comes from fp here, yeah, because there is an iso. Now fp obviously comes from some function f restricted to a neighborhood vp of p. Yeah, by definition of germ itself, it comes from some function f which is restricted on a small neighborhood vp around p. Yeah, vp is small enough. So we can also talk about the morphism from f of vp to g of vp. Yeah, this morphism we will call phi of vp. Yeah, in keeping with our convention of phi of u. So what is happening is, so the function f here, yeah, this gets mapped to phi of vp of f. Now this is same as g of p. Yeah, so this is same as g of p. Now the purpose of putting in this v of p, same in the sense means that they have the same germ on some smaller neighborhood. Yeah, you can replace vp by a smaller neighborhood. Now the purpose of putting in these vps is to cover the neighborhood u by these small sets vp. Yeah, so that is the standard trick we have been using. We take a small enough set, we take the neighborhood of a point p, and then take all the points in set u and cover u by a covering of these small neighborhoods. And on each vp we have this f restricted to vp, which is an element of f of vp. Yeah, so f restricted to vp is an element of f of vp. So if p and q are 2 points, yeah, then you talk about, say, a function f1 which is just f, which is just germ of f at P, but in a smaller neighborhood, Vp intersection Vq. And F2 says the germ of f at point Q, again in a small neighborhood, Vp intersection Vq. So suppose these are two very small things, but both of them are sent to, say, GV of P intersection Q. Yeah, see, these are two different sections. F1 is one section, F2 is one section, but they are both sent to G. Now by injectivity previously, we know that these two are equal. So P and Q are 2 points. We have two sections, say F1 and F2, and we want to show they come from the same function f. That will be true if F1 and F2 are sent to the same point in another neighborhood G of Vp by using injectivity. So you glue them together and get function f. Now the only thing remaining is we have to, f is in f of u, so phi of f is g. That is easy. You just consider function phi of f minus g. It is 0 on every small set, and then you just use the uniqueness property of Sheaves and say phi of f minus g is 0, which will give you phi of f equals to g. So on this slide we talk about kernels, co-kernels and images of morphisms of sheaves. Again, this is on page 63 of Hartshorne. So let this phi be a morphism of pre-sheaves. So this be a morphism of pre-sheaves. We want to define pre-sheaf kernel of phi, pre-sheaf co-kernel of phi, and pre-sheaf image of phi. So you have set V, which is a subset of U. Yeah, we have that injective map, and this is the following pre-sheaves we get. Kernel of phi of U. Obviously kernel is everything which gets mapped to 0. So obviously this kernel is nothing but a subset of sheaf F. And then we have co-kernel and image similarly. Yeah, so we have kernel pre-sheaf, co-kernel pre-sheaf, and image pre-sheaf. So the first pre-sheaf is a sheaf in general. Yeah, so the kernel pre-sheaf or pre-sheaf kernel of phi, this pre-sheaf is also a sheaf. Yeah, but pre-sheaf coker and pre-sheaf image are not sheaves. So image and coker are elements of G, which I have just written. So in general this is a sheaf. This is not a sheaf. And this is also not a sheaf. So we will show an example how we do not get the image as a sheaf. So first we cover an important notion of a skyscraper sheaf. So the example is, you first fix the point x of the space, big space X. And where the big space X is just the P1, the projective line, and Fx be a skyscraper sheaf at X. So we first need to explain what a skyscraper sheaf is. So skyscraper sheaf is just this entire line K, or the entire field K, if X is in U and it is 0 otherwise. So you take some set U open in P1 and say there are 2 points in U, X and Y, and X and Y you have the group K or the field K, but anywhere else you have 0. So if U just consists of 2 points X and Y, so you have K at X, K at Y, and you have 0 everywhere else, where K means the entire line. So you could say K as complex numbers. So I have drawn it also. So at set U you have this entire complex numbers, and it is 0 everywhere else. So just like a stock, so the stock is 0 everywhere except say certain finite number of points where it is the entire complex line. So we want to define now the direct sum of fx plus fy. This is nothing but the functions, instead of acting on set U, you are just restricting them to 2 points of U, x and y. Maybe x and y do not lie in U also. So you just have fixed 2 points, and you're talking about all the functions which are acting on set U intersection x comma y. Obviously these functions are defined on set U first. So basically it is an evaluation map at point x and y if they lie in U. So we now need to define from O of P1 to fx plus fy a map, so that we can then define the image. So you take an element f in OXU, it gets mapped to f, its restriction to x comma y. And let the G of U be the image sheaf. So we define a new sheaf, G of U as the image sheaf. And we need to show that this G of U is not a sheaf in general. It is a pre-sheaf, but it is not a sheaf. So this is nothing but the image of the above map. So this is a pre-sheaf on P1, but not a sheaf. So let us first take G of P1, the entire space. So the functions which are defined on entire OP1 are constants. So this is an important fact. The functions which are defined on the entire projective line are constants. So we can only have functions on part of the space, not the entire projective space. So this image map is iso to just this K, this closed field K. Yeah, because fx plus fy acting on P1 could be just K plus K. Yeah, and then you have a map from K to K plus K, which is iso to K. On the other hand, if you let u to be P1 minus x, and v to be P1 minus y, then g of u is K and g of v is K. Yeah, because g of u contains y, and we have this sheaf which takes value K only at x and y. So u contains y, so you have K. V contains x, so you have K. But u intersection v does not contain either x or y, therefore it is 0, because the sheaf you have takes value K at x or at y, and it is 0 everywhere else. So if there are two sections which are unequal, say S is 1, and K is complex numbers, so S is 1 and T is 2, and T is again from complex numbers, they obviously agree on G U intersection V because both of them are 0. But they cannot come from any single element. Yeah, there is no single element which is both equal to 1 and equal to 2. So we do not have a sheaf.